Okay, despite the announcement that I made for today's Wednesday lecture, this hour, there seems to be a problem from the side of students, maybe an examination or something like that. So regardless of the attendance, I still need to cover a few more things, and only afterwards our topic will be complete. So I will cover this and record it. I am recording it right now, and then put it on YouTube, and you are supposed to watch it, and you're responsible from the things that I will be covering for today. It's going to be only 1 hour. It's not a 2 hours lecture or anything. And I leave, I have closed the waiting room so anyone can attend in case they are finished and they try to attend the class. But regardless of that, whatever I will be talking about right now, you will be responsible. You will be responsible from the whole topics until the end of the Z transform anyway. So today I will start with an example, which is some sort of a true-false question, and true-false questions are very critical for these online examinations, right? Because many of the things will be like test questions and true-false questions, basically. So you're supposed to give correct answers to similar questions. The question is an analysis starting from a few observations. We have a system that is known to be causal and stable. Okay, we have this causal and stable system. So, and it's a discrete time, causal and stable system. Therefore, it has a Z transform, that is H of Z, and the corresponding impulse response, H of N. Okay. And we know that since it is causal, the region of convergence of H of Z is to the outside of some circle. And since it is also stable, it means that that region includes the unit circle. So the poles are inside the unit circle. It has a pole. This is an observation at Z is equal to 1/2. So as you see, it's inside the unit circle. A 0 at or on, it's not at actually, on the unit circle on Z is equal to 1, and other poles and zeros are unknown. So there may be other poles, there may be other zeros, or not maybe, and we don't know that. So the question is a true-false kind of question. Starting with part A, is this true or false? The Fourier transform of 1/2 to the power n, H of n, converges or exists? An interesting question, this one. How do we really relate or associate it with the observations that are given to you? So 1/2 to the power n is multiplying that. It essentially forces or enforces this H of n to have a region of convergence. So this is an observation that you have to make, and please try to understand why we conclude with such a thing. H of Z, region of convergence, must include something, and that something is Z is equal to 2 and outwards. Because if Z is equal to 2 is included in the region of convergence, then by multiplying with 1/2 to the power n, and we know that H of n is a right-hand sided signal, therefore 1/2 to the power n times h of n will make a suppression, a decaying exponential. It's a nice thing, but still the region of convergence must include z is equal to 2 point or radius and outwards. So the reason is that 1 over 2 will cancel with z is equal to 2 radius, and their cancellation will have 1, which will correspond to h of n sort of thing, or a convergent h of n. And in case h of n converges under those circumstances, then we will say that 1 over 2 to the power n h of n, therefore, will also converge. So this observation, now let's check. But the critical thing is this circle and onwards included in the region of convergence? And the answer to that question is it's a yes, because the region of convergence includes, it's not is, it includes z is equal to 1 and onwards, because it is causal and stable already. Therefore, out of the unit circle with 1 automatically includes the circle with a radius of 2 and outwards. Okay, that's natural. It already includes the unit circle, so magnitude of z or radius is equal to 2 is automatically included. So the answer to this is a big yes, it's true. You don't really need to elaborate this much. If you think of this in terms of a logic, you see that h of n Fourier transform already converges. So 1 over 2 to the power n, h of n is even better than that, because it's further multiplied with a decaying exponential towards the right-hand side, because it's causal, it's given causal. Therefore, even better than that, since Fourier transform of h of n converges, Fourier transform of 1 over 2 to the power n times h of n even better converges. So the answer to this part of the question is true. Part B, the Fourier transform of h of n, which is h of e to the j omega, is equal to 0 for some frequency omega. And again, from the definition that is given in the question, it's true, because there is a 0 on z is equal to 1. On the unit circle, there is a 0. And we know that the distance from the unit circle to the zeros will be in the numerator, the distance to the poles will be in the denominator. So if there's a 0 on the unit circle, the distance for some frequency value, for some angle value of omega, the distance will be 0. Therefore, h of e to the j omega will be obviously equal to 0. That's how we design filters. You may remember that one as well. So this is clearly true in a true and false question. Part C. H of n has finite duration. Now, the only way to have a finite duration h of n impulse response is only by the region of convergence to be the entire z plane, except z is equal to 0. So the question you have to ask for this is region of convergence the entire z plane? And since there is a pole at z is equal to 1 over 2, of course, it's not the entire z plane. It must be at least greater than radius greater than greater than 1 over 2. So if there is a pole other than z is equal to 0 or z is equal to infinity, if there is a finite pole on the z plane, the region of convergence must be bounded by that. So, and Therefore, it's not the entire z-plane. The region of convergence is not the entire z-plane. Cannot be. The answer is no. So h of n cannot be of finite duration. It must be extending towards infinity. So the answer is false to this part of the question. Part D of the question, h of n is real. Is this true or false? Now, for h of n to be real, h of z must be equal to h conjugate of z conjugate, or poles and zeros must appear in conjugate pairs. Are they appearing in conjugate pairs? There is a pole at 1/2. There is a zero at on the unit circle. We don't know where it is. So actually, we don't have the information to answer this question. We don't know the other poles. We don't know. Is the answer here, and we cannot really decide whether it's true or false. We cannot answer it. There must be a third choice, like cannot be determined or something like that. Cannot be determined or verified. We don't know whether it's true or false. The information is insufficient for that. Okay, now part E of the question. We have a g of n, which is a new system impulse response that is equal to n times h of n convolution with h of n. Strange. And this new system is stable and causal. Is it stable and causal is the new question. How can we do that? The best way to continue with this one is to make this observation. H of n convolution with h of n will have a z transform corresponding to h of z times h of z. So that is h square of z, or h of z altogether squared. Okay, we multiply it with itself. Then from here, n times this. Now we have to use the property of n times in the time domain corresponding to minus z times the derivative of the corresponding h of z, h square of z. Okay, this was a property that had, if you multiply a time signal by n, it means you are multiplying the z transform by minus z and taking the derivative. We are multiplying with the derivative of the previous z transform. Meanwhile, this right-hand side is equal to the minus z times the derivative of h squared of z, which is minus 2z times h of z times the derivative of h of z by chain rule of the derivative. Now, at this point, we can one by one make inspections. This one is only a zero at z is equal to 0. There is a 0. The poles and zeros of h of z are there. And again, from the previous property list, you may remember that when you take the derivative of a z transform expression, then the locations of the poles do not change, but they will be doubled. There will be two poles at the same position of the poles. So from here, the positions of poles do not change. Zeros are not important, but the poles, some poles are coming from h of z, and at the same place, some poles are coming from the derivative, and the poles are there, so they don't move in the coordinate axis of real and imaginary axis. So if h of n is causal and stable, h of n convolution of h of n will also be causal, and n times h of n convolution h of n will also be causal still. So everything will be causal, and the poles are at the same places. Causal means automatically, if h of n was originally stable, then this one will also become stable because the region of convergence, again, will include the unit circle. So we conclude that will be, the new thing will be causal and stable, really, because the positions of the poles don't really change. So the answer to this question is true. All right. This was an example true false question, which you may expect in an examination. That is quite soon. Right? Now, the next thing that I want to talk about very in brief is the block system or the block diagram representations. And we are very much comfortable with the block diagrams in discrete time because there is only one delay element that we will be using. The others are just scales, etc. So previously we were putting it like this. So the input is x of n and the output is x of n minus 1, a delay element like this. Now, the new representation for this one will be x. Let's not indicate the input and outputs, but it's just the block name that differs, and that is z to the minus 1. Z to the minus 1 means a delay, simple. So we will be using these, but with this kind of a new notation, it's quite an obvious notation. We will have to make a jump start, not from the simple block diagrams that we have seen in the first weeks of this course, but for example, we can do a more elaborate analysis for, let's say, feedback. Feedback is essentially the autoregressive or AR kind of a system, which works like this. There's an input X. You can call it X of n if you wish. And there is a forward path filter H1 that produces Y of n. And let's assume that this H1 has some poles which disables convergence, and therefore it's an unstable system. Let's assume that H1 is an unstable system. What is the way to stabilize it is through the concept of so-called feedback. So we put some portion of that Y of n, filter it further with H2, and then subtract it from the inputs. That feedback loop, it's a negative feedback loop because of this subtraction. So H2, or you could also use a plus sign in the feedback and put all the coefficients of H2 to become negative if you wish. It doesn't really matter which you do. But this kind of a feedback mechanism helps changing the poles. Originally, it was like, so the input is x of n. So originally, y of z was equal to h1 of z times x of z Okay, and H1 has some poles which are problematic, maybe out of the unit circle. Okay, so for a causal system, it means an unstable system. But now the new system appears to be altogether, if you consider this, like this. Maybe I should write it again. Y of z is equal to, in a large parentheses, h1 of z divided by 1 plus h1 of z times h2 of z times x of z. And the way to come up with this formula is very simple. You just have to see that we have x of z. Let's talk in z domain, because then it will correspond to multiplications and we will get rid of the convolution operators. X of z minus y of z times h2 of z altogether times h1 of z is equal to y of z is what you need to write. Maybe perhaps I should not be lazy about extracting this formula. It's actually very simple. In a different color, let me do it like x of z minus h2 of z times y of z altogether times h1 of z will be equal to y of z. Okay, that's what I'm saying. And that makes h1 of z, x of z. Let me keep it on the left-hand side of the equation, and let me put all the other y coefficients on the right-hand side of the equation, is equal to y of z plus h1 of z, h2 of z, y of z. Okay, and then putting into a parenthesis of y of z, the right-hand side becomes 1 plus h1 of z, h2 of z. And therefore, y of z divided by x of z, which is the overall transfer function that we put here, will be equal to h1 of z divided by 1 plus h1 of z, h2 of z. That's where the formula comes from. Now, typical feedbacks start from the simplest expression that we did as an example of z transform, and that is h of z is equal to the h of z, together with the feedback domain, feedback expression, is, let's say, 1 over 1 minus 1 over 2z inverse. Okay, this is a very well-known z transform, and let's assume that it's causal. Right-hand side solutions are of interest, so everything is physical, which means y of n minus 1 over 4 y of n minus 1 is equal to x of n, by the way, in terms of the difference equation. Okay, so these two are the same things. And in terms of the block diagrams, it actually appears like this: x going into a system, and the forward system is in the numerator, that is h1, and as you see, it is 1 over, so h1 is equal to 1. We don't have a system in the forward path. There is only a system in the feedback path, that is 1 over 4 z inverse. If you're uncomfortable with this kind of a notation, you could also separate 1 over 4 and z inverse from each other and put them separately on lines, but 1 over 4 z inverse is just a delay and a scaling factor of 1 over 4, and the output is y. So this is the feedback block diagram of the simple autoregressive system of h of z. Now let's extend from this example h of z is equal to 1 minus 2z inverse over 1 or minus 1 over 4 z inverse. Now this one is obviously a moving average, a numerator and a denominator. And whenever we do have these kinds of numerator and denominator businesses, it's usually practical to make a delay element to be shared between the numerator part, that is 1 minus 2z to the minus 1. So there's a z to the minus 1 over there. And in the denominator, there's another z to the minus 1. And the way to do this would be, I will use a different color, maybe the input and the denominator is the one that we are doing, let's say, which is telling me that there's a delay and it is multiplied by minus 2 and it is added to the input. Okay, so this comes from the numerator. Okay, excuse me. This is the numerator part. And the denominator part continues as a feedback. Maybe like this. There's a delay element, and then there's a factor of 1 over 4. And yeah, the output is, the input is x, the output is y. So this denominator part is now handled here. Okay, and we know that if you interchange these places, the orders of the orange and the red circled blocks, you can share the delay element. But this is something that you must already know from the first midterm. So we first make the feedback. We are using the linear and time invariant property of this of these. Sorry, this is 1 over 4 of these systems. So I first do the second part, and then do the first part like this. And clearly I can now share this delay element and make it just one delay element. And the simplest form, or the reduced form, is like this. There's only a single delay element at this point, and its output is going to the left and to the right. The left part is multiplied by 1 over 4 with a feedback. The right hand part is multiplied by minus 2, and there is a forward path here. So the input is x and the output is y. This is a first order simplified form. And it's already covered through the first midterm topics using d instead of z to the minus 1. So I'm not going into further analysis of this one, but I want to elaborate a little bit on another thing, which is second order systems, mostly using 3 types of realization: the direct realization, the parallel, and the series or cascade realizations. So in second order systems, the situation is exemplified. So let's do it on a numerical example because things will be easier to understand over there. H of z is equal to 1 over 1 plus 1 over 4 z to the minus 1 minus 1 over 8 z to the minus 2. It is second order, as you see, because the denominator z polynomial extends all the way up to z to the minus 2. And let's assume it's, again, causal. Is it stable or not? It depends on where the poles are. If you think of it as it is, then we will say that it's the third realization, unfortunately, because the other two will be easier to apply, which is called the direct realization. We will come back to this one. But before that, we will take a look at first a cascade or series representation, and then a parallel representation. The cascade representation requires the denominator to be split into first order systems like this: 1 plus 1 over 2 z to the minus 1 times 1 minus 1 over 4 z to the minus 1. So I factorize the second order polynomial into first order polynomial multiplications, and it also shows me where the poles are, because now I can see the poles. And a pole that I see is at minus 1 over 2, when z is equal to minus 1 over 2, it makes this denominator to be 0. So it's a pole. And at z is equal to 1 over 4, it also makes this time this part to be equal to 0 in the denominator. So it's also another pole. So the poles are at minus 1 over 2 and 1 over 4. And they are all less than 1 in magnitude. Therefore, since it is given to be a causal system, the region of convergence is to the out of the largest ring. The largest ring has a radius of 1 over 2 because there is a pole at minus 1 over 2. So the ring is at 1 over 2. Out of it will include the unit circle. So it is stable. And by the way, this way of looking at things will correspond to the type 1 realization, which is cascade. And finally, there is a third alternative, which is like this: 2 over 3 over 1 plus 1 over 2 z inverse plus 1 over 3 over 1 minus 1 over 4 z inverse. So it's a summation of two first order systems, and it's the second realization type, just parallel realization. So what are the cascade, parallel, and direct realizations in block diagrams? Let us draw them. The cascade realization is simple. There is a 1 over 1 over 1 plus 1 over 2 z inverse, the first part, this part, which will be very easy for us to draw. It's simply a delay times minus 1 over 2 with this kind of a feedback. And that makes the first part, 1 over 1 plus 1 over 2 z inverse part. And the output is further put into the second first order system, but that is here. Z to the minus 1. The feedback is 1 over 4. And there's a feedback. So this is realization number 1, the cascade realization. Two first order systems coming one after another. Therefore, they are multiplied in Z domain or in Fourier domain. 1 over 1 plus 1 over 2 Z inverse is multiplied by 1 over 1 minus 1 over 4 Z inverse, and this is the result. Now let's take a look at the parallel realization, which is not very much complicated either, but probably it will be the longest in terms of drawing. We have a 2/3. So let me do the scaling after. So I'm doing this, okay? But I'm doing 1/1 plus 1/2 z inverse. And then I will multiply by 2/3, all right? That's what I'm gonna do. 1/1 plus 1/2 z inverse will be this. The delay is scale of -1/2, and feedback, that is 1/1 plus 1/2 z inverse. And the output of this one is scaled further by 2/3. This is one branch. And there is another branch which works like this: 1/3 times 1/1 minus 1/4 z inverse. So I'm going to do 1/1 minus 1/4 z inverse with the same input. So I take a branch from the same input and I construct my feedback like this. And the output of it is multiplied further by 1/3, because in the numerator there was a 1/3. And finally, I have to combine these two outputs. This is X, this is Y, okay? This is realization number 2, which is a parallel implementation. All right. Now it's time to take a look at the direct implementation, which is probably the most interesting one. So how can we do it that way? Because the direct implementations will help us to make minimal realizations with the minimum number of delay elements if there is further numerator coefficient. And I will also do an example for that one as well. So, but for this one, I will do a standalone example of the third direct realization. And it's going to be like this. Maybe we are losing the formula. So let me copy the formula in a parentheses here so that it will be with us while drawing. It was this. This is the input-output H of Z realization that we are trying to draw in the third realization. So now let's do it. We have an X coming in, and the output is Y, and Y is first delayed by the delay element, and its output is scaled by -1/4. Normally, of course, it must be combined to the top branch, but it will further be combined from the bottom excuse me, with another further delay, z to the -1 again. So from here to here, actually, it's like z to the -2 times y of z, or the signal at this point will be notated as y of n-2. You can also think of it like that. And that output is multiplied by the negative of -1/8, which is +1/8, actually. And this is the overall realization, the direct realization. Look at how the coefficients change. This z to the -1 term appears first, and its sign is negated to -1/4. And then this z to the -2 coefficient appears here as 1/8, which is the negative of -1/8, and they are combined as a shortcut. And this is the third realization. Now let's try to see these realizations all together, although it will be a little bit small. As you see, the three types of realizations in the feedback loop, that is the autoregressive part. Okay, now let me do an example where I will only continue with the direct implementation, although there is, of course, a series and a parallel implementation that are simply available. But I will do the direct implementation because it will help me to show you altogether the reduced form with the minimum number of delay elements. So that's an example. And h of z is equal to 1 minus 7/4 z to the -1 minus 1/2 z to the -2 over 1 plus 1/4 z to the -1 minus 1/8 z to the -2. By the way, notice that the denominator is exactly the same as the previous example because it helps me to split the formalism, and the direct form of the denominator is already given here. It's at the top of the page. But how about rightwards going branches? What will it be? First, let me show you the availability of the cascade form. In the cascade form, it's actually like this. This is one alternative of doing it. It's 1 plus 1/4 z to the -1 over 1 plus 1/2 z to the -1 times 1 minus 2 z to the -1 over 1 minus 1/4 z to the -1. Now, you may notice that the choice of which factorization to use with the first factorization of the denominator is just arbitrary. I could equally say that this over this times this over this. So it's just an arbitrary choice, but this is one of them only. And I'm not going to draw it anyway, because, for example, for this one, the answer of the realization is already given. It's here. Okay. And then the output of this one will be fed into another form which really looks like the same or similar structure, the same structure. And that will correspond to the cascade implementation. So this one is almost done, we can say. The other one is a parallel implementation where we will have two first-order systems, which can start from this. But unfortunately, there's a dangling numerical coefficient of 4 appearing over there. So I will explain you how to handle it. So this is the parallel form, and I'm assuming that it's done as well because we have this first order system, which we know how to do, how to handle. We have this first order. So the outputs will be just, this one must be, the second one must be subtracted from the top branch. And there's a 4. How can you do that? It's very simple. You put an extra branch from the input to the output and scale by 4 and add them all together at the output stage. So from the input, it splits into 3 parts and then gets combined at the output. The parts are, one of them is trivial. It's just a scale of 4. The other one is a first order system, and the third one is also another first order system. You just combine them at the output. Clearly, the interesting realization is the direct form realization. And I really want to show you that one at the right-hand side of this page. Meanwhile, keeping the formula on the corner here, so that you will understand how to immediately draw such things for the numerator polynomial divided by denominator polynomial. And I'm skipping a lot of details of changing their size and sharing the delay elements and all that. The input is here. Oops, I'm sorry, it's just jumped. Maybe I should make it a little bit smaller. And here I have the delay. And the delay output will split to the left and to the right. To the left, it's the denominator part, which is the negative of the coefficient of z to the minus 1, that is minus 1 over 4. And again, another delay element. And its output goes to the left and to the right. To the left, it's the negative of z to the minus 2 coefficient, that is minus 1 over 8. Negative of it is 1 over 8. And we are accumulating from the left branch. From the right branch, the coefficients signs are staying. This one is negative 7 over 4. And the last one of z to the minus 2's coefficient here is minus 1 over 2. So let's keep it there. And then accumulate. And the output is y. So try to make a screen capture of this input-output realization using delay elements and amplifiers or attenuators, some scaling operators, in other words. This is the direct form, type 3 direct form. Okay. The others, this one was type 1, this one was type 2, which I'm not gonna go into the details because they are clearly available. Now this last direct form, I want to emphasize something for you to notice, that this part, that is the feedback going part, is essentially the same as this part, okay? It's the same because this denominator is the same as this denominator, okay? So the denominators will go towards left-hand side like this. All right, now that concludes all the discussions regarding our regular Z-transform topics. Now, just like the unilateral Laplace transform and the bilateral Laplace transform business, we have a similar business in the Z-transform domain, and we have the unilateral Z-transform too. And to differentiate between the normal bilateral means two-sided, the regular two-sided Z-transform, where the summation is from minus infinity to plus infinity, like the integration of the Laplace transform from minus infinity to infinity. That is the bilateral or the normal transform. For the Z-transform, it's the normal Z-transform. There is a unilateral one which starts from 0 and goes to infinity. So it's only one-sided one. That's why it's called unilateral, single-sided. I will notate it as a subscript of u, just like I did for the Laplace transform, like this, x sub u of z, which is the unilateral z transform. In the book, it uses some calligraphic X shape for the unilateral transforms, both for the Laplace and the Z transform. The unilateral X, curly and calligraphic way of writing the X will be corresponding to the unilateral transforms, but I cannot draw it that way, so I put a subscript of U to indicate the one-sided or unilateral transform. And the definition of this one-sided is, as the name suggests, it's from 0 to infinity only, x of n times z to the minus n. Originally, it was from minus infinity to infinity. So in many cases, xu of n, x sub u of z, sorry, and x of z are, they may be the same. They are the same for all x of n's that are already right-hand sided, because then the summation automatically starts from 0 and extends to infinity. But for left-hand sided things, it's a problem. So the unilateral Z transform does not handle left-hand sided signals or signals where the indices are at -1, -2, -3, etc. It does not handle that. So how does it solve the difference equations then? Well, since there is no left-hand sided information, those informations must be injected into the Z transform through so-called initial conditions, just like the unilateral Laplace transforms initial conditions. You have to know what is, for example, x of 0. What's the initial condition? Without the knowledge of initial condition, you cannot really invert the unilateral Laplace transform. And depending on the orders, essentially the number of initial conditions must increase. What do we mean by that? By the way, the region of convergence for the unilateral Z transform is not ambiguous. It cannot be inside a circle. Okay, it's not allowed. It's always out of a circle, because all the signals that we are handling are intrinsically right-hand sided signals. So there's no ambiguity of region of convergence versus right-hand sided solution versus left-hand sided solution, etc. We don't have that kind of a situation. But it has its advantages. The advantage is there's no ambiguity of region of convergence. But the disadvantage is now we have to use the initial conditions all the time. Like x of n minus 1, for instance, the unilateral Z transform, so I will use it like uz. Originally, the double-sided arrow is supposed to have the Z over there, which is a transform pair. On the left-hand side, there's this time signal. On the right-hand side, I write the Z transform. But now I'm indicating that the right-hand side is the unilateral Z transform. So if I shift like, not n minus 1, but n plus 1, which is essentially the shift in the other direction. So we are losing some information. That information must be injected into the system like this. First of all, Z times xu of Z, this much is what we had as a property already. But since it's the unilateral Laplace, the unilateral Z transform, now I must have the initial condition, that is Z times x of 0, which is the initial condition at n is equal to 0. That pretty much resembles what is happening in the derivative expressions of unilateral Laplace transforms. So you can think of it that way. Now, since you will not be responsible from the unilateral Z transform, this example is not very much critical for you, and this information is not very much critical for you in terms of answering any questions in the final, because I'm not going to ask it. But of course you need to know it, because without knowing, if you encounter this kind of a new expression, you will be very much surprised for the unilateral transforms, especially for the unilateral Laplace transform, because it's more common to use unilateral Laplace transform than the bilateral Laplace transform that we have seen, particularly in control systems and differential equations. Now, so I will just show you one example of how to attack a solution. The example is as follows. We have a difference equation, like a differential equation. Okay. And we have an initial condition of y of -1 to be equal to beta. This is the initial condition. And x of n is alpha times u of n. So I'm applying a unit step, okay, to the system, and I want to determine what is the output, what is y of z. And for that, I need to take the z transform, the unilateral z transform of this difference equation with this initial condition and this input, which will be like this: yu of z plus 3 times, in parentheses, I will have to open z to the -1 yu of z plus beta, because this is the overall z transform of y of n minus 1 with the initial condition at y of -1, which is beta. And 3 is multiplying all of them, because 3 is multiplying y of n minus 1. And the right-hand side is the input in z domain. So I have to write the z transform of alpha times u of n. The z transform of u of n is 1 over 1 minus z inverse. It's like 1 to the power n times u of n. So 1 to the power n is alpha to the power n with alpha equals 1. And when you put alpha is equal to 1 here, you see it like this. It's 1 minus z to the -1. It's the inverse of the first difference, right? What was the first difference? It was 1 minus z to the -1. Inverse of that will correspond to the unit step. And alpha times that. So it's alpha over 1 minus z inverse. And from there, y of z can be obtained as, of course, I have to think of expanding the equation, multiplying with everything, putting into parentheses of y of z at the left-hand side, and then the right-hand side will be something, that something divided by the parentheses will correspond to y of z. And after expanding it, it will be like this. As simple as that. You can further try to split this into addition of two first-order systems, but that's not necessary. It's not our point. I would really like to emphasize, however, one thing here. This beta appears to be in here only, which is meaning that this is the response of the system with no input. The input is just alpha times u of n. If alpha is 0, for instance, if there is no input, then y of z will be equal to this one. That can be considered as the zero input response, which is kind of the homogeneous part. Whereas this one, this part is not related to the initial condition, beta. So here We are only observing the input. So if the initial condition of beta was equal to 0, then we wouldn't have this one, and we would only have this part, which is called the zero state response. Okay. Something like a particular solution. So this is all I would like to really emphasize and give an example regarding the unilateral Z transform. In fact, I could give you a second order system with two initial conditions too, or that would give you a better example of how to incorporate the initial conditions into higher order difference equations. Well, clearly you would have to have y of -2 this time. A further y of -2 would be necessary. Y of -3 would also be necessary. If the orders are second or the third order or the fourth order, you need a y of -4. Okay, these initial conditions would be required for solving difference equations, but this much example, I think, is sufficient to give you a glimpse of the existence of the unilateral Z transform. And since you won't be responsible from that, I want to really stop at this point and look no further as an example. This unilateral transforms are out of your concern for the final examination, but you have to study well for the regular things. In the exams, you will be allowed to print out copies of the tables, the transform tables, typical transform pairs in Fourier, in Euler's expansion, in discrete time or continuous time Fourier transform, Fourier series, the Laplace transform, and the Z transform too. So all the tables that you may think of from the book will be available to you in the examination, but nothing else. And you're not allowed to cheat from other resources, okay, during the examination. So I want to stop at this point, and I'm wishing you good luck in your final examinations and hope everything works out well for you. Take care. Goodbye.